Hey guys, welcome to a new set of notes. Today we're going to be talking about stellar evolution. So stars go through a birth, life, and death cycle, and we're going to talk about each one of those stages. So stars are born in what's called an interstellar clump of matter. It's generally called a nebula, which most people are familiar with that term, or nebulae for more than one. It's full of dust and gases, and those things are what combine to eventually make planets and stars. The clouds cool and condense enough for hydrogen atoms to join together into, oh, that should say helium atoms on your screen. I apologize. So helium atoms or molecules. In the Milky Way, clouds are about 92% hydrogen, 7% helium, and 1% other molecules, elements like carbon, carbon monoxide, things like that. In the nebulae, particles are widely dispersed despite having hundreds of times the amount of mass compared to just a singular planet or star. Very dense areas of the nebulae attract more particles over time until a real gravitational field can be formed and can be consistent. The hydrogen or the clouds begin to collapse on itself from immense pressure, and a furnace inside of that cloud starts to ignite. That's your nucleosynthesis, and a star or a ball of hot gases is born. That life cycle continues and becomes the balance or a balance between gravity, trying to shrink the star together, and the output from that furnace, from that nucleosynthesis, and trying to make it grow. So it's a careful balance between the two. All right, the first stage is the protostar stage. Once this cloud has collapsed, or the nebula has collapsed in, gravitational energy converts to thermal energy. So gravity becomes heat. So you get your increase in temperature, and you get your red light, which is long wavelength from the energy, but not enough to fully engage a functioning fusion process. The gravity picks up its pace and it heats up internally, and it kind of keeps going through that cycle. Once it hits about 10 million Kelvin degrees, or degrees Kelvin, the heat and pressure is so intense that that's when the 4 hydrogen nuclei that we talked about in the last section fuse together to form helium, which is specifically hydrogen fusion. Main sequence stage is the next part that it goes into. This is where heat and motion from that protostar create that outward force. Remember, heated gas actually expands. If you want, you can think of like a balloon. If you blow it up with your own hot air, the balloon kind of deflates after it cools down a bit. That's because the gas is cooling and condensing. Once there's a balance between gravity and gas pressure, you have a stable star. That's the balance we mentioned a couple slides ago. There's very, very minimal changes in size or output of energy. That's why we call it a balance. There are 3 types of main sequence stars. You have a hot or a high mass blue star. It burns through its hydrogen extremely fast, in that fast being a few million years. You have the smallest star, a red one, that takes hundreds of billions of years to burn through. And you have a yellow star, an intermediate mass, which burns through in approximately 10 billion years. Our sun is a yellow star. It's actually a very small yellow star. They call it a yellow dwarf. And it's only about 5 billion years old. So we're about halfway through its life cycle right now. Stars spend about 90% of their life in this stage. So this is the main sequence. When we talk about red giants, this is where we start to run out of hydrogen fuel, so that there can't be any more of the hydrogen fusion. It leaves behind a helium core. There's no more fuel. That gravity starts to be the winning force and starts to collapse the star in. The collapsing creates much more thermal energy because you're putting a lot more pressure, and the pressure was turning into thermal. And then it heats up the very hydrogen-rich shell and bloats it out, and it burns even faster. So when it bloats, it just increasingly expands. When our star bloats, it's going to encompass at least the first two planets, Mercury and Venus. Most likely it will possibly reach out to Earth as well. With a main sequence, the red giant is an intermediate mass, so this is what our star becomes. It becomes, for about 1 billion years to become a red giant, and it's about 100 times larger than it currently is. When you have a supergiant or high mass star, it's about 1,000 times larger. So those bigger stars we talked about in the main sequence become supergiants. They are red due to the large surface area. When you have more surface area, it can cool down a lot faster, kind of like the sun sweating. Temperatures reach above 100 million degrees Kelvin in the core, causing the 3 helium nuclei to make a carbon nucleus. Hydrogen and helium are then consumed for energy, and even heavier elements than carbon are made. So that's where you get your oxygen, magnesium, silicon, everything in that early part of the periodic table. Once it all fuses into iron, which we even did one of those problems the other day, once it all fuses into iron, the sun or the star cannot create any more energy. It's done. All right. Which leads us to burnout and death of a star. So low mass stars, they're also called the red dwarfs, are the most common in the universe. They remain stable for about 100 billion years and longer. They never become hot enough to fully ignite helium, so it never goes through that bloating and getting larger sequence. It just shrinks into a hot, dense white dwarf. Intermediate mass stars, like our sun, blow off their bloated atmospheres with the expanding clouds of gas and become what's called a tiny white dwarf in the center of a planetary nebula. So that that gas and everything is still is blown off from the sun, but it still settles within our area or our universe, or sorry, galaxy. So it still settles, and then we have this tiny white dwarf in the center instead of a nice pretty yellow sun. When you have a high mass star, it's a very short lifespan that explodes into a supernova. Supernova is full of gas and debris. Stars become millions of times brighter, and those are often some of the really fun pictures that you get to see of the nebulas like this one, and then the supernovas where there's just the different colors and it looks like an explosion has gone off. So you have a video to watch. This is one that needs to be played through the internet browser. It will not play through the PowerPoint. And then after you watch that and answer the questions in your packet, this may help you out a little bit with some of your classwork over the next couple days. So that is all I have for you guys.